Okay guys, welcome to our third tutorial. So in this one we're going to go over how exactly to design a drive based on Swift drives. So Swift drives are basically the drives that we use right now for our team. So they are made by Swift, they're highly modular, which makes them pretty good compared to the Go Builder option, though the bad part of it is that it lacks a lot of customality. It's not that customable as the Go Builder mechanical wheels. So as we transition to the next couple of seasons, these will become obsolete because we cannot use the motors in these anymore. But at least for the next couple of seasons, we'll be continuing to use these Swift drives because we spent like 400, 500 bucks on these. So as you can see here, this is a Swift website about the Swift Drive V2s. So as you can see here, you can see a lot of information about these drives, but these are, you can look at these on your own time if you want to, basically. So they have a lot of configurations for us to use, but we'll skip ahead. So the main interesting parts is these. So like the assembly video is like where you assemble the drive wheels. Um, we've already assembled them basically. So the CAD and drawings is a Google Drive folder, which has the CAD for the frame kits and the drive modules. So the on-chip configurator is basically a document which you can kind of basically configure the plates as you want to. It's just like kind of a template for the Swift drive base. But you can see here basically like this. Then the drivetrain simulator, it basically kind of simulates basically how well this drivetrain is going to perform. But we'll keep this for later, basically. So let's start designing. So essentially, our usually for FTC, the starting configuration is normally bounded in 18 inch by 18 inch by 18 inch, or at least this season, which is around 457 millimeters. So if we go onto the Go Builder website, we can try to find an aluminum channel that is close to 457 for the largest drivetrain we can have. So in this scenario, we're going to go for a large drivetrain, but like in a lot of other cases, a smaller one will be lighter and more compact and sometimes advantageous, so you need to consider that. So, yeah. So in this case, I'm going to use the low side U channel because this is what Swift uses in their official thing. So as you can see here, for this one, in this example, this is wait, this is weird. Sorry. This thing's entirely black, which is this thing is 17 inches. So 17, which is approximately what we want actually. So we can count how many holes is this on the diagonal side, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 holes. Great. This is 16 holes. I hope this is 16 holes. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, 16 holes. So basically we're going to be using this low side U channel, but what we're doing here is a bit different from the official thing. So the official thing is just basically this frame kit, but what we're going to do is a parallel plate drive, which is kind of similar to our robot this in the decode season, but you can see an example here of what does a parallel plate drive looks like. So it basically looks like this. There are two plates that constrain the wheel, and it is usually rather highly modular. So in these cases, these use Go Builder motors, but we use Swyft because we chose Swyft to like kind of save some time, basically. Oh, so here is this one, essentially. See parallel plates. For this one, it's just kind of simplified as this is like going to be more modular for teams that are just starting basically, because they can configure them easily. But we're cooler than that, so we're going to start making our own parallel plates. So essentially, the hard part of this is that for Swyft, their drawings are not that great. For instance, as you can see here, so well, you can sort of tell like the mounting hole pattern on this thing, but you can't really tell the like you can see here that there is this kind of shape, not fully circular shape. This is not really documented on there, but we're going to keep this shape sort of in mind as we go. So we're going to need to import the wheels and kind of make sketches based on that. So we're going to go into detail a bit later. So let's create a document. Swyft drive trim. So here it is. So go to Assembly tab, and then we can insert a Swyft drive. So it's been quite a bit of time since I did this, but let me see. I think it should be in other robotics vendors. Actually, this is weird. If it's not in here, actually we can just import from other documents. So for example, I own this, which is which I'm just gonna make this example. I'm gonna just make a copy of this to import the wheel. So copy this. So we're gonna import the wheel using that. Or you can go into make a copy of their RI3D design. But essentially, they don't really have a part specifically for like the wheel, I think, to be specific, which is kind of the frustrating part. So I can maybe save some more time by just going into that document. Yep. So this is the RI3D design by Swyft. Basically, they designed this robot in 3 days of the game release. So this is basically using Swyft drives. So we're gonna wait until this load and figure out what name is this Swyft thingy here. Swyft drives here. So I'm gonna wait a second. Yeah, I know this tutorial is gonna be rather long because we're gonna make a drivetrain in one go. And yeah. So as you can see, this thing is highly compact, as the motor, half of the motor is actually inside the wheel, essentially. Okay, motor. Okay, I guess they did not have that as a complete part, so that is the horrible part of this. So, we can go with the other option. So another fun thing that you can notice is that these plates from Swyft actually are what we're kind of looking for. If you look here. Please wait a second. Yeah, So as you can see here, this is actually the mounting pattern here. So what we can do with this is that we can just basically just, well, kind of, we can basically kind of copy over these the outside edges of this and kind of just produce the pattern artificially. So I'm going to show you how to do this in a second. So let's do this. Recently opened. And I'm going to import this. So as you can see here, that this thing is only basically almost 3/4 of a drive base. So we kind of want a bit more than this. So what we're going to do is we're going to create a make connector, which you do Control+M. And yeah, you choose like the center. If you can't choose center, press Shift, and then you can choose this. So this is the center of the thing. So then what we're going to do after this is that we're going to create a part based on this thing. Let's see. Create part student in context. Boom. Yes. And then there we are. So then we can go on the top plane, start sketching. So what we're going to do in this case is that we're going to select this. You don't need to press anything, just click on all of this. You have to click one by one. And you can project, convert it, or just press U. So now it's going to be converted. So one thing to note is that we're going to basically just flip mirror this over this line. So we're going to have a line that helps us do it. So if you create a line and then press Q to make it a construction line. So construction lines, they don't actually become involved in like the actual part making. They're like just here to help us. So you can just do this to the center of here, press M to delete this part basically. It kind of went a bit sketchy, but you can just make this vertical. Press V, make this vertical. So it's going to be fully constrained, not blue anymore. So then after this, what you can do is that you can press mirror, choose a mirror line. So this is going to be a mirror line. Press this, and then copy all of this. Boom, hooray. Oh, I also forgot to do this. So we're going to mirror this too. Boom, we went off the design. So this is basically the basis that we want to have. So then next, we need our other wheel here. So as you know, the maximum space we have is around 457 millimeters. So we can kind of use this as a guide. So we want to, like, using this plate from Swyft as a guide. So we kind of want this to be one end and another end to be like on the other side and approach around 457. So we can use our example from this year. Where is it? Artificial intelligence. So this is our CAD from this year. And let's see how long we actually place the thing. It might take a while. I'm sorry for this. Actually, I can just open this, perhaps? Okay, never mind, this thing loaded.